Hey guys, so you just watched a video on elephant's toothpaste reaction, which is a super fun chemistry demonstration. Hopefully, when I find my hydrogen peroxide, we can do it together. But in the meantime, as I'm still unpacking stuff, I'm sorry, I don't know where it is at the moment. But let's dive deeper into the chemistry that they were talking about. So here's the reaction of hydrogen peroxide. This is actually the same stuff that you put on your cuts when you get a boo-boo. And it manages to kill a lot of the bacteria that is in your cut. And what happens is H2O2 naturally reacts just with itself to form water and oxygen. So basically, it just breaks down over time to form these products. So, but in the video, what you watched, they had to mix a few different things. So, what exactly were they doing? Well, they added soap to the mixture. That was just for fun. The soap didn't actually do anything spectacular other than capture the oxygen gas so that it would look like this really cool steaming foam. So the soap just made it foamy. And they also added a catalyst called potassium iodide, Ki, and it was a catalyst. Do catalysts go in the chemical reaction? If so, where should I write it? The answer is no. Catalysts do not actually go in on the reactant side or on the product side. Instead, you would express this catalyst over the arrow, saying that potassium iodide, or you could just do iodide by itself, since that's the main component that we care about, that was used to help speed up this reaction. So pretty much as soon as they poured in that potassium iodide, all of a sudden the elephant's toothpaste quite literally exploded out of the container. Without that potassium iodide, you actually still had this reaction going on. H2O2 was breaking down into just water and oxygen gas. It was just doing it very, very slowly, which is not exciting to watch. That's actually why you store peroxide in a kind of dark container, because it helps to limit the breaking down of this unstable compound. So you'll almost always, if you go into your cabinet, you'll see it in a dark container. But let's look at the chemical reaction in terms of its potential energy diagram. So here I'm going to draw my diagram. On the y-axis, I'm going to put my potential energy. And on the x-axis, that's our reaction coordinate, reaction. And so overall, this is the line, the potential energy line of the reactants. And in the case of this reaction, this is the only reactant, the H2O2. Now, for the products, should I draw the line up here or down here? If I draw the line up top, that is considered to have gained energy because the potential energy would have increased from the reactants to the products. So that means that you are putting heat or some kind of energy into the system being, the bucket where they have the hydrogen peroxide. Did they heat it up? No. So the correct answer, and this would look like this is an endothermic reaction where you're adding heat, endothermic, and you would have a delta H that's positive. But that is not what happened. Sorry, my voice. Instead, what we saw was a highly exothermic reaction. And how did we know it was highly exothermic and that the energy went down? So from our original starting point, the overall energy of the products is lower than the reactants products. So what that means is that in forming the products, going from reactants to products, the system lost energy to the surroundings. And you saw it in the video as a lot of heat or steam coming off of it. So obviously you weren't there, or maybe you were, what do I know? But you probably saw it was kind of like steaming. So it was hot. So the delta H, this is an exothermic reaction because it's giving off heat, exothermic. So the delta H is negative, meaning overall it lost energy and it's going down. So here is the basics of the potential energy diagram. So based on the notes that you took on potential energy, what did the catalyst, the potassium iodide that I have over the arrow, what did that do for the reaction? So the normal reaction, you have an activation energy that is quite high. You have to go from here all the way up. That's how much energy that you need to go over the hill. It's kind of like, running a race. Like here's the starting line and here's the finish line. And in order to really you're putting the most energy in where you're going up the hill. Once you're at the top, you could essentially just roll down the hill, and it's really easy to just roll down it. But going over or to the top of the hill, that's the amount of active energy you had to put in. So this is the activation energy right here. And so what happens to that activation energy when I add a catalyst like potassium iodide? Does it make it harder? Ooh, I meant to erase that. Does it make it harder to run up the hill to get to the product side, the finish line? Or does it make it easier? So the correct answer is that it makes it easier. So you still start with the same amount of energy, but the only thing that changes is that your hill gets a little bit smaller. In the case of this reaction, it got substantially smaller. This is not drawn to scale. So we had a smaller hill, which makes it a lot easier to run over. So now the activation energy is only this little portion instead of the original, which went all the way to the top. So this right here is, this is the new reaction pathway. Notice how both the energy of the reactants and the energy of the products did not change at all. It's just this middle part, the race itself, that got lower. So all it did was it made this actual chemical reaction happen quicker. It was just easier, but it didn't affect the overall reactants and it didn't affect the overall products. Over a long period of time, this would have formed anyway, the H2O2. The peroxide would have broken down. It just would have taken a really long time. So when you're at the very top of your hill, where you're at the top with your activation energy, this top part is called the activated complex. Activated complex. Activated complex. What that means is that's exactly at the point where you are between being in both reactant land and product land. So you're actually kind of a conglomerate of all of it. It's all just kind of in the process of reacting. So this is right in the middle of the reaction. And so it's a complex, That is both between what reactants look like and what products look like. So just to emphasize one other thing, the difference between the energy of the reactants overall and the product's energy overall, this is your delta H. So since overall the reactants went from this amount of energy down to this amount of energy, that delta H is negative. That's how I figured that out. In an endothermic reaction, it would be the same thing, but positive. All right.